The observable universe holds more galaxies than every grain of sand on Earth. These island universes are living entities with secret lives of birth, growth, and death. By the end of this journey, you will understand the entire cosmic story, from the first spark of light to the final fading of the stars. We will uncover how invisible dark matter sculpts reality, and why the violent death of one galaxy can give life to another. How do you picture the final fate of our own Milky Way? That primordial darkness was not destined to last. Across the emptiness, a profound transformation was beginning, sparked by the most fragile of seeds. In the first fleeting moments of the universe, microscopic quantum ripples were inflated to staggering sizes, imprinting the cosmos with a faint blueprint of structure. These tiny wrinkles in spacetime became the gravitational wells where everything would eventually gather. An unseen architect, dark matter, began weaving this blueprint into a vast cosmic web, an invisible skeleton stretching across the emptiness. Ordinary matter, the protons and electrons that would become us, was simply along for the ride, drawn into the deepening pools of gravity these dark matter halos created. Within these dense, dark knots, the first clouds of hydrogen and helium gas started to cool, their particles slowly succumbing to the relentless pull. And then, in the profound black, a spark, the first star ignited, a solitary beacon tearing through the eternal night. This was the cosmic dawn, a period when the universe switched on its lights for the very first time. These first stars were not like our sun. They were colossal, raging furnaces, hundreds of times more massive, living brilliant and brief lives before exploding in cataclysmic supernova. Their violent death seeded the cosmos with the first heavy elements, the very stuff of planets and life. These explosions also forged the first proto-galaxies, small, chaotic clumps of stars and gas swirling within their dark matter cocoons. They were the humble beginnings of a galactic empire, the first whispers of the grand story to come. But how did these initial fragments evolve into the majestic spirals and glowing ellipticals we see today? The journey from cosmic infancy to maturity was a turbulent and dramatic one. That silent architect, dark matter, never rests. Picture it crafting an invisible framework, a cosmic skeleton upon which the entire visible universe is built. Though we cannot see it or touch it, this mysterious substance makes up about 85% of all the mass in the cosmos. Its presence is felt only through gravity, the ghostly hand that shapes everything we see. Dark matter forms immense spherical halos around the locations of future galaxies. These halos act as deep gravitational wells, natural traps for the ordinary matter swirling in the void. Without this dark scaffolding, clouds of hydrogen and helium gas would simply drift apart, scattered by the primordial energies of the young universe. Galaxies as we know them would never have been born. It is within these stable, massive halos that gas can finally settle, cool down, and begin the slow process of condensation. As the gas pools and grows denser, it fragments, giving birth to the very first stars. The specific characteristics of the dark matter halo itself are what decide a galaxy's destiny. The total mass of the halo dictates how large a galaxy can grow. The way that mass is distributed and how it spins determines whether the galaxy will become a majestic, flat spiral or a vast, round elliptical. This invisible component is the true puppet master of galactic evolution, orchestrating the entire dance of stars and gas from the shadows. Its enigmatic nature forces us to ask, what were the initial conditions that set a galaxy, any galaxy, on its unique path toward maturity? What tiny fluctuations in the ancient cosmos decided our own Milky Way's spiral fate? Deep within those primordial clouds, a threshold was crossed. The first stars did not just form, they erupted into being. These were the population 3 stars, titans of a lost age, built from nothing but the universe's original ingredients, hydrogen and helium. Without any heavier elements to help them cool, they collapsed into monstrous sizes, some reaching several hundred times the mass of our own Sun. Their birth was a furious, rapid-fire event inside the first protogalaxies, which were little more than chaotic, swirling nurseries of gas and newborn suns. The arrival of these stellar giants flooded the cosmos with a new kind of energy, an intense ultraviolet light that began to tear apart the neutral hydrogen atoms filling space. This was the Epoch of Re-ionization, a pivotal chapter that burned away the cosmic fog and permanently changed the universe from opaque to transparent, finally ending the Dark Ages. But such immense power came at a cost. These stars lived fast and died young, their brilliant lives culminating in cataclysmic supernova explosions. In their violent deaths, they forged and scattered the first heavy elements across the void, atoms like carbon and oxygen, the very building blocks of planets and life. This was the first great act of cosmic pollution, enriching the pristine gas clouds and forever altering the recipe for the next generation of stars. The legacy of these initial sparks is written into the chemical fingerprint of every star born since. So how did these chaotic, enriched fragments begin to build the more structured, majestic galaxies we recognize today? The universe's chaotic infancy gave way to a stunning maturity, a cosmos filled with galaxies of every shape and size. Edwin Hubble, gazing into the depths of space, saw an underlying order in this apparent chaos and devised a simple but powerful way to classify them, a system we now call the Hubble sequence. At first glance, it looks like a simple fork in the cosmic road. On one path, you find the magnificent spiral galaxies. Think of our own Milky Way, a vast, spinning pinwheel of stars. Its defining features are a bright, central bulge and majestic, curving arms that spiral outward, traced by luminous blue clusters of young stars and glowing pink nebulae where new suns are being born. This is a galaxy still under construction, rich with the cold gas needed to fuel future generations of stars. The other main path leads to the elliptical galaxies. These are the cosmic elders, appearing as vast, featureless spheres or ovals of stars. They lack the flat disk and dramatic arms of their spiral cousins. Their populations are typically older, cooler, and redder, having long ago exhausted their reservoirs of star-forming gas. Their quiet, steady glow speaks of a history where the frenetic pace of creation has largely ceased. And then there are the galaxies that defy this neat classification entirely, the irregulars. These are the cosmic misfits, often showing distorted, fragmented shapes that bear the clear marks of a recent gravitational encounter, a close pass or collision with another galaxy. This stunning diversity is not a random assortment. A galaxy's place in the Hubble sequence is a direct reflection of its life story, a fossil record written in starlight. Its initial mass, its rate of star formation, and crucially, its interactions with the cosmic environment all sculpt its final form. A spiral galaxy majestic disk can be violently disrupted by a merger, its gas compressed and rapidly consumed in a burst of new stars, potentially transforming it into an elliptical. An isolated, quiet existence allows a spiral to preserve its structure and continue its slow, steady star formation. The Hubble sequence is thus much more than a simple catalogue. It is a family album capturing galaxies at different stages of their lives, their shapes revealing chapters of solitude, conflict, and transformation. The key to unlocking these evolutionary secrets lies in understanding a galaxy's social life, the dramatic encounters that can redefine its very existence. A galaxy's life is rarely a solitary journey. Across the vast expanses of space, these stellar cities are drawn together into clusters and long, weaving filaments, creating a dynamic cosmic society. This constant gravitational interaction means that close encounters are not just possible, they are inevitable. When two galaxies swing into each other's vicinity, they begin a billion-year dance choreographed by gravity. Their spiral arms stretch and distort into long, flowing tidal tails of stars and gas, creating breathtaking celestial bridges and plumes. This beautiful chaos, however, is profoundly violent. The collision compresses immense reservoirs of hydrogen gas, triggering firestorms of starbirth known as starbursts. Entire clusters of brilliant, blue stars ignite in a frantic, short-lived blaze, a dramatic but unsustainable burst of creation that can rapidly consume a galaxy's fuel. This stellar frenzy is often followed by an even more profound event. The supermassive black holes lurking at the hearts of both galaxies are stirred from their slumber. Drawn together by friction and gravity, they sink toward the center of the newly merged galaxy, eventually orbiting one another in a final, fateful duet. Their eventual collision sends ripples through the very fabric of space-time, gravitational waves that echo the most powerful event since the Big Bang. The ultimate outcome of such a major merger is a complete galactic transformation. Two beautiful, star-forming spiral disks are utterly destroyed, their structures blended and randomized into a new, much larger object, a smooth, red and dead elliptical galaxy. This is cosmic cannibalism on the grandest scale. Even smaller, dwarf galaxies are not safe, often being torn apart and consumed by their larger neighbors, their stars added to the halo of the dominant galaxy. This dynamic interplay of attraction and destruction is a primary engine of galactic evolution. A galaxy's shape, size, and even its future are profoundly shaped by its social life. And at the very center of this newly forged galaxy, the merged supermassive black hole awakens, becoming the heart of a powerful new engine that can dictate the galaxy's fate for eons to come. That merged black hole awakens to become the galaxy's ultimate ruler. At the heart of nearly every massive galaxy, including our own Milky Way, lies a supermassive black hole, a gravitational abyss containing the mass of millions or even billions of suns compressed into a single point. For much of a galaxy's life, this monster slumbers in quiet darkness. But when a galaxy provides it with a feast, everything changes. As vast clouds of gas and dust spiral inward, they form a seething, frantic whirlpool around the black hole called an accretion disk. Friction within this disk heats the material to millions of degrees, causing it to glow with a light that can outshine every star in the galaxy combined. This is an active galactic nucleus, or AN, a cosmic lighthouse whose brilliance can be seen clear across the universe. In the most extreme cases, the black hole's immense magnetic fields channel some of the infalling matter into two narrow, powerful jets. These jets erupt from the poles at nearly the speed of light, punching through the galaxy and shooting out into intergalactic space for thousands of light years. This incredible release of energy is not just a spectacular light show. It is a fundamental regulatory force known as AGN feedback. The intense radiation and these colossal jets act like a cosmic blowtorch, heating the galaxy's vast reservoirs of cold gas or blowing them away entirely into the void. Without this cold gas, the galaxy can no longer form new stars. The AGN effectively strangles its own host, putting a swift end to the era of starbirth. This reveals a deeply symbiotic, almost self-regulating relationship. the growth of the central black hole is entirely dependent on the galaxy feeding it gas. Yet, once the black hole grows powerful enough, its Aegean phase unleashes an fury that stops that feeding process, ultimately halting the galaxy's growth and its own. The largest, most massive elliptical galaxies we see today, the red and dead worlds, are likely the products of this precise cycle. Their central black holes grew to such immense proportions through past mergers and feasting that their resulting Aegean outbursts permanently shut down their star-forming factories. The heart of darkness, therefore, is not just a destructive force. It is a key architect of galactic maturity, a paradoxical guardian that brings a violent end to a galaxy's youth, forcing it into a quiet, stable, and long retirement. These stellar nurseries are not gentle places. They are violent, chaotic, and breathtakingly beautiful workshops where the raw material of the universe is forged into new suns. Deep within a galaxy's spiral arms, immense clouds of molecular gas and dust drift like cosmic ghosts. These nebulae are frigid and dark, but they hold the potential for brilliance. A slight disturbance is all it takes, perhaps the shock wave from a distant supernova or the gravitational nudge of a passing spiral arm. This disturbance pushes the cloud past a critical point, and gravity, the master sculptor, takes over. It causes pockets within the cloud to collapse inward, the gas and dust falling into a growing core. As these cores spin and accrete more material, they heat up, becoming protostars. When the core temperature reaches millions of degrees, nuclear fusion ignites, and a new star officially joins the galaxy. The most famous example is the Orion Nebula, a stellar factory visible to the naked eye, where hundreds of young stars are blazing to life within a glowing cloud of gas. The most massive of these newborn stars are incredibly influential. They shine with ferocious intensity, emitting powerful stellar winds that blast away the surrounding gas, sculpting vast cavities and pillars. Their lives are a brief, million-year flash, ending in titanic supernova explosions. These cataclysmic deaths do more than just scatter newly forged heavy elements. They send violent shock waves rippling through the nebula, compressing other regions of gas and triggering the birth of the next stellar generation. This self-perpetuating cycle is the heartbeat of a galaxy. The rate at which a galaxy forms new stars is its most vital sign, a direct measure of its health and activity. A galaxy rich with cold gas, like a classic spiral, can sustain a steady, gentle pace of star birth for billions of years. But a galactic collision, as we saw, acts like a defibrillator, shocking the entire system and causing a frantic, explosive starburst that can consume its fuel reserves in a relatively short cosmic time. This continuous cycle of stellar birth and death is what slowly changes a galaxy's very essence. Each generation of stars fuses hydrogen and helium into heavier elements like carbon, oxygen, and iron. When those stars die, they seed the surrounding gas with these elements, enriching it. The next generation of stars and any planets that form around them are born from this richer material. Over eons, a galaxy's chemical composition evolves, becoming more metal-rich. This slow enrichment is a primary driver of a galaxy's evolutionary path, guiding it from a youthful, gas-rich spiral to a mature, quiescent elliptical. The story of a galaxy is, therefore, written in the life and death of its stars. But what happens when this cycle finally runs its course? What fate awaits a galaxy when its last stellar nursery goes dark and the final generation of stars begins to fade? The death of a star is not an end, but a dispersal of cosmic ingredients. Every supernova explosion acts as a galactic forge, creating elements far heavier than the hydrogen and helium of the primordial universe and scattering them across the interstellar void. This process, known as chemical enrichment, is the slow, steady metamorphosis of a galaxy's very essence. The first generation of stars lived and died in a universe of perfect simplicity, their composition limited to those two basic elements. But when they exploded, they seeded the cosmos with the first metals, a term astronomers use for any element heavier than helium. This enriched gas then coalesced to form the next stellar generation, each new star born with a slightly higher metallicity than the one before. Our own Sun is a product of this long chain of stellar life and death, a metal-rich star that formed from gas polluted by countless supernovae that came before it. This chemical evolution leaves a distinct fingerprint on a galaxy, a record written in the light of its stars that we can read with our telescopes. In massive elliptical galaxies, which experienced a frenzied burst of early star formation, nearly all the stars are old and metal-rich, their gas having been quickly processed and consumed. In a spiral galaxy like our Milky Way, the story is more complex. The central bulge is dominated by older, metal-rich stars, while the outer disk and halo still contain ancient, metal-poor stars that are relics from the galaxy's youthful days. This gradient is a timeline, telling us that the inner regions formed stars more efficiently and rapidly, enriching themselves quickly, while the outskirts developed more slowly, preserving some of the original, pristine material. This galactic lifeblood, the ever-increasing metallicity, does more than just color a galaxy's history. It directly shapes the potential for new worlds. The heavy elements forged in stellar cores are the very stuff of rocky planets. A cloud of pure hydrogen and helium could only form gas giants, but a cloud enriched with silicon, iron, and carbon can coalesce into terrestrial worlds like Earth. The increasing abundance of these metals over cosmic time made the universe progressively more hospitable to planets like our own. The iron in our blood and the calcium in our bones were literally forged in the hearts of long-dead stars, then scattered by their violent deaths to one day become part of our world. We are, in the most profound sense, children of galactic enrichment. This raises a haunting question about the ultimate fate of all galaxies. A destiny written not in starlight, but in the relentless pull of gravity and the slow exhaustion of cosmic fuel. Our own cosmic home, the Milky Way, offers a front-row seat to the galactic drama. This vast island of stars is not merely our address but a living case study, a barred spiral whose structure tells the story of its long and violent life. Look up on a clear, dark night, and that faint milky band arching across the sky is the plane of our galactic disk, seen from within. We reside within one of its majestic spiral arms, a stellar suburb orbiting a bustling center. That center is marked by a dense central bulge, a spherical swarm of mostly old red stars, many rich with metals forged in earlier cosmic epochs. Surrounding this entire structure is an immense, faint halo of ancient stars and mysterious dark matter, a ghostly relic of the galaxy's deepest past. By mapping the ages, motions, and chemical compositions of the stars around us, astronomers can read this galactic autobiography. They have discovered that the Milky Way is a product of a violent history of cosmic cannibalism. Faint streams of stars arcing through the halo are the galactic ghosts of dwarf galaxies long ago torn apart and consumed by our galaxy's immense gravity. Each of these mergers added stars and gas, helping to build the majestic spiral we call home today. At the very heart of the bulge, hidden by thick clouds of dust, lies the supermassive black hole Sagittarius, a star. This silent gravitational anchor, with a mass 4 million times that of our Sun, is a sleeping giant whose past activity has likely shaped the entire central region. Our galaxy is a dynamic system, with vibrant Starbirth still lighting up its spiral arms while its ancient halo whispers tales of its violent youth. This intimate, local knowledge is our key to the cosmos. By understanding the life cycle of the Milky Way in exquisite detail, we gain a universal template. We can look at a distant, faint spiral galaxy whose light began its journey to Earth billions of years ago and understand the processes that shaped it. We are not just living in a galaxy, we are studying it from the inside out, using our home to decipher the lives of all island universes. But if our own galaxy has grown through such dramatic mergers, what does this violent past tell us about its ultimate future? This profound connection between light and time gives us our most powerful tool for unraveling the galactic story. Because light travels at a fixed, finite speed, the photons striking the mirror of a telescope today began their journey across the cosmos millions or even billions of years ago. When you look at the Andromeda galaxy with binoculars, you are not seeing it as it is now, but as it was 2.5 million years ago. We are forever looking into the past. This simple, staggering fact transforms every telescope into a time machine. Instruments like the Hubble and James Webb Space Telescopes are our portals to earlier cosmic eras. They do not just show us distant objects, they allow us to witness history itself. The most dramatic demonstration of this is the Hubble Deep Field. Astronomers pointed the telescope at what appeared to be a tiny, empty patch of dark sky, a space no larger than a grain of sand held at arm's length. For days, it collected the faintest trickles of light. The resulting image was not darkness, but a universe teeming with thousands of galaxies, each a smudge of light from a different moment in cosmic history. Some of these galaxies are seen as they were when the universe was less than 1 billion years old. They are not the grand spirals and ellipticals of today. They are small, irregular, and chaotic, often little more than fragmented clumps of brilliant blue stars, still in the process of assembling themselves. This is the universe's family photo album, a chronological record of galactic growth. By comparing these ancient snapshots with mature galaxies nearby, we can watch the entire narrative unfold. We see the early universe was a far more violent and dynamic place, with frequent collisions and ferocious rates of star formation. These galactic building blocks slowly merged, growing in size and settling into more stable, structured forms over billions of years. This direct observational evidence is how we test our theories. We can run sophisticated computer simulations of galaxy formation, starting with the conditions just after the Big Bang, and then check if the virtual galaxies our models produce look like the real ones we see in these deep field images at corresponding epochs. It is a constant process of prediction and observation, refining our understanding of how dark matter halos gathered gas, how supernova enriched it with metals, and how black holes eventually quenched star formation. This ability to peer back through time confirms that the driving forces of galactic maturation are not just theoretical. They are etched into the light of the cosmos, a historical record we are only just learning to read. And as we trace this story from the first proto-galaxies to the present, we are forced to confront the ultimate destiny that awaits all galaxies, a fate dictated by the same forces that gave them life. A galaxy's turbulent youth eventually gives way to a long, stable adulthood. This mature phase is a state of delicate equilibrium, a cosmic balancing act between creation and consumption. For a spiral galaxy like our Milky Way, maturity looks like a well-ordered system. Its majestic disk rotates with a stately rhythm, its spiral arms tracing regions where star formation continues at a steady, sustainable pace. This is not the frantic starburst of a merger, but a gentle, ongoing process. New stars are born just fast enough to replace those that die, with the galaxy's reserves of cold gas being slowly replenished by a trickle of pristine material falling in from the intergalactic medium. Its structure is fully realized, a clear division between the central bulge of old stars, the star-forming disk, and the vast, faint halo. This is a galaxy in its prime, a harmonious engine converting gas into starlight across billions of years. For an elliptical galaxy, maturity has a very different character. It is a state of quiescence, a cosmic retirement. The frenetic star-forming fireworks of its violent past, likely triggered by a major merger, have long since subsided. Its vast reservoirs of cold gas have been utterly exhausted, either rapidly forged into stars during a final burst or blown away into intergalactic space by the powerful outburst of its central black hole. Without this raw material, the galaxy's star formation has effectively ceased. What remains is a population of aging stars, mostly long-lived red dwarfs and older, cooler suns, glowing with a collective reddish hue. This galaxy is a fossil, its current appearance a direct and frozen record of its entire history. Its smooth, featureless shape is the ultimate signature of a past cataclysm that randomized the orbits of all its stars. This hard-won equilibrium, however, is not a permanent destiny. It is a fragile truce that can be shattered at any moment. A close encounter with a neighboring galaxy or a fresh merger can send a new flood of cold gas rushing into the system, violently reigniting star formation and awakening the sleeping supermassive black hole at its heart. This can plunge the galaxy back into a period of intense activity, effectively resetting its evolutionary clock. Even internal processes, like a new episode of AGN feedback, can disrupt the balance by heating or expelling the very gas that fuels the galaxy's gentle growth. A mature galaxy's quiet grace is therefore a temporary chapter, a calm between the storms of its violent birth and the inevitable changes still to come. What external forces, then, could possibly bring an end to this billions-year reign of stability? This vibrant engine of creation cannot run forever. A galaxy's future is written in the dwindling reserves of its most precious resource, the cold, dense gas that fuels the birth of new stars. Like a great forest slowly consuming its own soil, a galaxy lives by turning its raw material into stellar generations. With every new star that ignites, a little more of this fuel is permanently locked away. Most of it ends up in long-lived, low-mass stars like red dwarfs, which will shine for trillions of years, effectively sequestering that gas from the galactic economy. Other fractions are converted into the dense, dark remnants of dead stars, white dwarfs, neutron stars, and black holes, cosmic vaults from which the material will never return. But consumption is only part of the story. The galaxy's own most energetic processes actively sabotage its future. The furious winds from supernova explosions can blow vast quantities of gas clear out of the galactic disk, ejecting it into the intergalactic void. This is a galactic hemorrhage, a loss of potential on an unimaginable scale. Yet even this stellar fury is often overshadowed by the power of the galaxy's central black hole. When active, its AGN outbursts act as the ultimate regulatory mechanism. The intense radiation and relativistic jets heat the surrounding gas to millions of degrees, making it so energetic that it cannot cool down and collapse. This hot halo of gas simply cannot form new stars. In some cases, the AGN's power is so immense it doesn't just heat the gas, it drives it out of the galaxy entirely, permanently cutting off the star-forming supply. This is the Great Quenching, the moment a galaxy's star formation rate plummets. The brilliant blue glow of young star clusters fades, replaced by the steady, redder light of an aging stellar population. The galaxy is not dying in a dramatic collapse, but settling into a long, quiet senescence. Its most vibrant period is over. How, then, does this slow fade play out across the different types of galaxies we see in the universe today? For the smallest galaxies, the end is not a dramatic collapse but a slow, quiet fade into darkness. These cosmic dwarfs are the most common galaxies in the universe, yet they are tragically fragile, their faint light easily extinguished. Their greatest weakness is their shallow gravity. Unlike a massive galaxy that can hold onto its gas against powerful forces, a dwarf galaxy's gravitational grip is tenuous at best. The very first supernova to explode within them can be catastrophic. The shock waves from these stellar deaths act like a cosmic pressure washer, easily blowing the entire reservoir of star-forming gas out into the void. Robbed of its lifeblood, the dwarf galaxy's star formation is permanently quenched. It becomes a ghostly relic, a collection of aging stars that will slowly dim over billions of years, never to create a new sun again. This gentle fading is one path to galactic death, but there is another, more violent end for these small systems. When a dwarf galaxy drifts too close to a colossal neighbor like the Milky Way, it faces a process of gravitational dissection. The difference in their gravitational pull from one side of the dwarf to the other creates immense tidal forces. These tides act like a cosmic hand, relentlessly pulling and stretching the smaller galaxy. Its outer layers of stars and gas are the first to be torn away, stripped from their home and flung into long, looping rivers of debris that orbit the giant galaxy. We see this happening right in our own cosmic backyard. The large and small Magellanic Clouds, those two fuzzy patches of light visible from the southern hemisphere, are not permanent companions. They are dwarf galaxies caught in the Milky Way's gravitational web. As they swing around our galaxy, their gas is being violently stripped, forming a vast, invisible ribbon known as the Magellanic Stream that trails behind them across the sky. This stream is a ghost in the making, the visible evidence of these galaxies being slowly torn apart. Their stars will eventually be scattered into the Milky Way's halo, their identity erased as they are absorbed. This slow, tidal death is a fundamental feature of the cosmic food chain. The largest galaxies grow not only by merging with equals, but by consuming a steady diet of dwarfs, their growth built upon the dismantled remains of countless smaller systems. This raises a profound question about the ultimate fate of all galaxies, large and small, as the universe itself continues its relentless expansion. This serene red glow is the final color of a galaxy's life. Astronomers categorize galaxies on a simple but profound chart known as the color magnitude diagram, and the most massive galaxies inevitably migrate to a zone called the red sequence. This is not a place of vibrant creation, but of quiet permanence. The inhabitants of this sequence are the universe's retired giants, the colossal elliptical galaxies that have run out of fuel. Their brilliant blue O and B-type stars, the massive, short-lived beacons that give spirals their bright arms, have all vanished. These stellar titans burned through their hydrogen in mere millions of years, exploding as supernova and leaving no new generations to replace them. What remains is a population of older, more frugal stars. The galaxy's collective light is now dominated by the steady, reddish glow of aging red giants and the countless main sequence stars similar to our own sun, which will shine reliably for billions of years to come. These galaxies are cosmic retirement homes, vast collections of suns quietly burning through their remaining nuclear fuel. Their evolution has not stopped, but it has slowed to a near standstill. They can persist in this state for time spans that dwarf the current age of the universe, their populations slowly dimming as the lowest mass stars finally begin to flicker out. This peaceful reddening, however, masks a ferocious origin. A galaxy does not arrive at this quiet end through a gentle decline. It is often the direct result of a catastrophic past, a major merger that acted like a final, glorious fireworks show. Such a collision funnels enormous amounts of gas into the galactic core, igniting a firestorm of star formation that consumes the entire remaining gas reserve in a relatively short cosmic burst. This final starburst creates a brilliant but brief blue phase, quickly followed by the inevitable reddening as the last massive blue stars die. The resulting galaxy is left gas-poor, its stellar orbits randomized by the violent encounter into the smooth, featureless ellipsoid we see today. The red sequence is therefore the ultimate signature of a completed life cycle, a galaxy that has lived through its most turbulent chapters and settled into a long, uneventful twilight. This green valley is a cosmic crossroads, a final farewell to vibrant life for many spiral galaxies. It represents a critical transitional phase, a slow fade from the brilliant blue cloud of active star formation into the permanent red sequence of galactic retirement. A galaxy does not leap from one state to the other. It traverses this intermediate zone over billions of years. Its color literally shifts in this phase, the overall hue of its starlight changing from a youthful blue to an aging red. This color change is a direct symptom of a deeper malaise. The frantic production of massive, hot, blue stars has slowed to a trickle, and without these brilliant new beacons to dominate the light, the cooler, redder glow of the galaxy's older stellar population begins to take over. The galaxy is in a state of profound metamorphosis, losing its defining characteristic on its way to becoming a passive system. But what forces push a galaxy onto this one-way path? The causes are varied and often work in concert. A simple, internal cause is the gradual depletion of its cold gas reserves. After billions of years of steady star formation, the galaxy may simply be running out of fuel, like a great fire burning through its last logs. Another internal process is known as morphological quenching. Here, the galaxy's own majestic structure becomes its undoing. As a spiral galaxy's central bulge grows massive and stable, its gravitational influence can prevent the remaining gas in the disk from collapsing easily. The gas is stabilized, starved of the density fluctuations needed to trigger the birth of new stars. External forces can be even more brutal. If a spiral galaxy lies within a dense cluster of galaxies, it can experience a phenomenon called ram pressure stripping. As the galaxy moves at high speed through the thin, hot gas that fills the cluster, this intergalactic medium acts like a powerful cosmic wind, violently blowing the galaxy's own star-forming gas right out of its disk. The galaxy is stripped bare, its future stolen by its environment. The time a galaxy spends crossing this green valley and the precise mechanisms that guide it are among the most active questions in astronomy today. Understanding this transition is crucial because it reveals how star formation is systematically shut down across the universe. Often, this final act involves the galaxy's central supermassive black hole awakening for one last decisive performance, a final regulatory event that seals the galaxy's fate. This supermassive black hole is more than a monster, it is a master of cosmic balance. Think of it as a galactic thermostat, a self-regulating engine that prevents its own home from burning too hot or growing too cold. This elegant process is known as AGN feedback, and it is the key to understanding why the universe is not filled with impossibly gigantic galaxies. The cycle begins with the very star formation that gives a galaxy its light. As new stars ignite, some of the leftover gas inevitably spirals inward, drawn by the immense gravity of the central black hole. This infalling gas does not vanish silently into the abyss. Instead, it forms a seething, luminous accretion disk, turning the black hole into an active galactic nucleus, a beacon of raw power. The energy released is staggering, a torrent of radiation, and in many cases, twin jets of plasma screaming into space at nearly the speed of light. This outburst is the thermostat kicking on. The intense radiation and heat from the AGN pour into the galaxy's vast reservoir of surrounding gas. This gas, which would otherwise cool down, condense, and fall back into the galaxy to create billions of new stars, is instead superheated. It becomes too energetic to collapse, effectively putting star formation on hold. The AGN has slammed the brakes on the galaxy's own growth. This creates a beautiful, self-correcting loop. If the galaxy forms too many stars too quickly, it sends more fuel to the black hole, which activates the AGN more powerfully, which then more effectively shuts down star formation. It is a built-in governor, ensuring a galaxy does not consume its entire gas supply in a single, brief burst of cosmic glory. This feedback mechanism elegantly explains a profound mystery astronomers have observed for decades: the tight correlation between the mass of a galaxy's central bulge and the mass of its supermassive black hole. The two grew up together, their fates locked in a gravitational dance. The black hole did not just grow randomly, it grew in proportion to the galaxy that fed it, and then it used its power to dictate when that feeding would end. In this way, the heart of darkness is not merely a destroyer. It is a paradoxical guardian, a force born from the galaxy that ultimately helps to quench it, guiding its evolution toward a stable and long-lasting maturity. This delicate dance between creation and suppression is the final piece that explains the life cycle of the most massive galaxies in our universe. This invisible wind shapes the destiny of galaxies in the most crowded corners of the cosmos. Within a dense cluster, thousands of galaxies swarm like bees, all moving at incredible speeds through a superheated, thin gas known as the intracluster medium. For a spiral galaxy on a high-speed journey through this environment, the experience is violently transformative. The galaxy plows through this diffuse, million-degree gas, and the resulting force is immense, a cosmic gale known as ram pressure. Picture a bicyclist racing downhill, feeling a powerful headwind pushing against them. Now amplify that sensation to a galactic scale, where the wind is not made of air, but of searing plasma. This relentless pressure acts directly on the galaxy's most vital asset, its reservoirs of cold, dense hydrogen gas. The galaxy's own gravity struggles to hold onto this star-forming fuel as the intergalactic wind simply blows it away. The gas is torn from the galaxy's spiral arms, leaving behind a system that is suddenly, tragically impoverished. We can witness this brutal process in action with objects like the jellyfish galaxy J0206. In stunning telescopic images, it looks exactly like its namesake, a cosmic creature with long, streaming tentacles of gas being forcibly stripped from its body. These luminous tails are not made of stars, but of the galaxy's very lifeblood, its future potential for new suns, being ripped away into the void. The quenching of star formation in this scenario is not a slow, internal fade. It is a rapid, external execution. A spiral galaxy can be stripped of its gas in just a few 100 million years, a blink of an eye on cosmic timescales. Its vibrant blue spiral arms, once glowing with young star clusters, will quickly dim and redden as the last of its massive blue stars die out, leaving no new generations to replace them. The galaxy is left as a passive, red system, its structure perhaps still intact but its spirit of creation extinguished. Ram pressure stripping is a stark reminder that a galaxy's fate is not determined by its internal nature alone. Its location in the cosmic web is everything. In the universe's dense urban centers, this environmental force is a dominant killer, efficiently shutting down star formation and adding another red, dead galaxy to the cluster's population. This raises a chilling question about the ultimate future of all galactic structures, not just from external threats, but from the internal decay of their own stellar populations over timescales that defy comprehension. This process of galactic cannibalism is the final chapter for countless island universes. In the dense urban cores of galaxy clusters, a single giant often reigns supreme, a CD galaxy of such immense size it defies simple comprehension. These are the supergiant ellipticals, cosmic predators that sit at the gravitational center of thousands of other galaxies. Their growth is not through gentle accretion, but through a relentless diet of their neighbors. Any smaller galaxy, a spiral or a dwarf, that drifts within the central giant's sphere of influence is caught in an inescapable trap. The difference in gravity is so vast that the smaller galaxy is slowly, methodically torn apart over billions of years. Its stars are stripped away not in a single violent event, but in a long, drawn-out tidal shredding. These stolen stars do not vanish. They become part of the giant's extended stellar halo, a faint, enormous glow that can stretch for millions of light years. This halo is the ghostly archive of the giant's cannibalistic history, a cemetery of digested galaxies whose individual identities have been completely erased. Their stars are now simply part of the collective, orbiting the central behemoth. This is hierarchical merging in its final, most extreme form. The first small protogalaxies merged to build spirals. Those spirals then collided to form larger ellipticals. Now, in the crowded cluster environment, the largest elliptical of all continues to grow by consuming every galaxy that dares to come too close. A CD galaxy can ultimately contain trillions of stars, a number so large it surpasses the population of many small galaxies combined. This is the ultimate fate for a great many galaxies, to have their structure dissolved and their starlight absorbed into a greater whole. It is a cosmic dissolution, the loss of self for the growth of a leviathan. What does this relentless consumption tell us about the far, far future of all galactic structures, when the universe is old and cold and the lights begin to go out one by one? This relentless consumption unfolds against a backdrop of an even grander and more permanent transformation. The fate of every galaxy is ultimately written not just by gravity, but by a mysterious, repulsive force known as dark energy. This enigmatic component of the cosmos, which we cannot see or touch, behaves like an anti-gravity, causing the expansion of the universe to accelerate over time. For billions of years, gravity has been the dominant architect, pulling matter together to build galaxies and clusters. But as the universe grows older and more diffuse, dark energy's push is beginning to overwhelm gravity's pull on the largest scales. Imagine space itself as a stretching fabric, with the threads between galaxy clusters being pulled apart faster and faster. Galaxies that are not gravitationally bound to one another, like islands in an ever-widening ocean, will find themselves carried away from each other at speeds that eventually surpass the speed of light. This does not mean they are moving through space faster than light, but that the space between us and them is expanding so rapidly that their light can no longer bridge the growing chasm. One by one, these distant galaxies will vanish over a cosmic horizon, their light fading to black, their signals lost to us forever. The observable universe, which today teems with billions of galaxies, will slowly empty. Our own Milky Way, Andromeda, and their satellite galaxies, all bound together as the local group, will remain as a single, isolated island in an immense and growing void. We will be marooned in a small, gravitationally bound family, while the rest of the cosmic empire recedes into an unreachable past. The grand narrative of galactic evolution will not stop within these isolated groups. Mergers will still occur, stars will continue to be born from remaining gas, and black holes will eventually awaken. But the overarching story of the cosmos, the great dance of clusters and filaments that has defined its structure for billions of years, will be over. Dark energy sets the ultimate stage, a vast and silent arena where the final, isolated acts of galactic life will play out in profound and permanent solitude. That final stellar generation will be the last. Trillions of years into the future, the universe's star-forming era will have drawn to a permanent close. Every galaxy, from the mightiest elliptical to the faintest dwarf, will have exhausted its last reserves of cold, dense gas. The great cosmic factories that once blazed with the light of newborn suns will have fallen silent forever. Without this raw material, the magnificent cycle of stellar birth and death, the very heartbeat of a galaxy, will finally cease. What remains is a universe entering its final, quietest chapter. The most massive stars, the brilliant blue giants, will have vanished eons ago in spectacular supernova explosions. Medium-mass stars like our own Sun will have long since shed their outer layers, leaving behind their dense, Earth-sized cores as white dwarfs, celestial embers slowly cooling in the dark. The last lights in the cosmos will be the smallest and most frugal of stars, the red dwarfs. These faint, crimson suns are so efficient with their nuclear fuel that they can shine for trillions of years. But even their immense endurance has a limit. One by one, they too will finally exhaust their hydrogen, dimming and cooling into another population of blackened white dwarfs. The universe will then be a collection of stellar corpses, a cosmic graveyard populated by white dwarfs, neutron stars, and black holes. All of these remnants will share one inevitable fate: to steadily radiate away their last vestiges of heat, cooling toward the absolute cold of the background space. This is the state of maximum entropy, often called the heat death of the universe. It is not a dramatic explosion or a violent collapse, but the ultimate stillness that comes when every energy gradient has been leveled, when no more work can be done, and no more complex processes can occur. In this distant epoch, the galaxies will still exist as gravitational structures. The dark matter halos that gave them birth will still hold the stellar remnants in their grasp. But these will be dark, frozen islands. The once majestic spiral arms will be invisible. The brilliant central bulges a memory. There will be no more blue nebulae, no more golden star clusters, no more light at all except the faint, fading infrared glow of cooling dwarfs. The vibrant cycles of galactic life, the violent mergers, the brilliant starbirth, and the black hole eruptions will all have run their course. This is the lonely, quiet end of the story, a cosmic graveyard where the once vibrant lives of galaxies have reached their final, silent rest. Yet even against this backdrop of finality, a radical question emerges. Could the story of the galaxies ever truly begin again? Some theoretical models dare to challenge the permanence of the heat death with a hypothesis of cosmic rebirth. Imagine an endless, rhythmic dance of existence, a cyclic universe model where the cosmos undergoes perpetual cycles of expansion and contraction. In this vision, the eventual collapse, triggered when dark energy's influence wanes or reverses, does not end in a crushing singularity of infinite density. Instead, it leads to a big bounce. The universe rebounds, transforming the energy of its own implosion into a new Big Bang, a fresh fiery genesis. All the matter and energy, the scattered atoms of long-dead stars and the dust of forgotten galaxies would be recycled. The entire magnificent process of cosmic structure formation would start over from scratch, potentially giving rise to new galactic empires built from the ashes of the old. An even more speculative idea looks to the strange rules of quantum mechanics in the far, far future. In the near-perfect vacuum of an eternally expanding universe, quantum fluctuations could, given spans of time so vast they defy comprehension, spontaneously give rise to new universes or restart local regions of activity in a process known as quantum tunneling. A new cosmos could bubble into existence from the absolute nothingness of the old. However, within our current and most strongly supported standard model of cosmology, which includes dark energy's relentless push toward eternal expansion, a universal rebirth is not predicted. The evidence we have gathered points overwhelmingly toward a one-way journey from a hot, dense beginning to a cold, dilute end. This very finality gives profound meaning to the galactic life cycles we witness today. The birth of a spiral galaxy, the fiery merger that forges an elliptical, the brilliant but brief life of a massive star, these are not scenes in an endless, repeating play. They are part of a unique and non-repeatable chapter in cosmic history, a single, grand narrative that unfolds only once. Even our most detailed models of galactic life leave profound gaps in the cosmic story. Scattered throughout the universe are ghostly islands known as ultra-diffuse galaxies, or UDG, and their very existence defies simple classification. These cosmic phantoms are the size of our entire Milky Way, yet they contain only about 1% of its stars. If our galaxy were a bustling, luminous metropolis, a UDG would be a sprawling, dark countryside with only a few scattered streetlights, its vast structure barely visible against the blackness of space. Their discovery was a monumental challenge, requiring powerful telescopes to detect these faint, wispy smudges against the void. The central puzzle is how such large, fluffy structures ever came to be. One compelling theory suggests these are failed galaxies. Imagine a primordial cloud of gas beginning to collapse within its dark matter halo, poised to become a new spiral. But before it could form a dense disk and ignite billions of stars, a traumatic event stripped away its gas. Perhaps a nearby galaxy's gravitational pull siphoned it off, or the heat from a nearby cluster of galaxies prevented the gas from ever cooling. The result is a galaxy-sized framework that never fulfilled its stellar potential, a cosmic blueprint that was never built. Another possibility paints a more violent picture. A normal, healthy spiral galaxy could have a close encounter with a giant neighbor. The gravitational tides would not tear it apart completely, but they would pull and stretch it, puffing it up into a vast, diffuse cloud while robbing it of its star-forming gas. This would leave behind a galactic ghost, the bloated and faded remnant of a once vibrant system. The deepest mystery surrounding UDGs involves their dark matter. Does a galaxy this large and faint still possess a massive Milky Way-sized dark matter halo anchoring it? Or was its dark matter also stripped away, leaving it a fragile, ghostly shell? The answer could completely reshape our understanding of how dark matter governs a galaxy's formation and resilience. Solving the riddle of ultra-diffuse galaxies is more than just filling a niche in our catalogs. It forces us to question the fundamental rules linking dark matter to visible starlight and reveals that the pathways of galactic evolution are far more diverse and strange than we ever imagined. What other faint, forgotten giants are lurking in the darkness, waiting to challenge our cosmic narrative? Woven through the fabric of a galaxy is another invisible force, one far more subtle than gravity but no less influential. Galactic magnetic fields permeate the vast spaces between stars, a cosmic web of force that guides the flow of matter and energy. While incredibly weak by human standards, these fields are a fundamental component of the interstellar ecosystem. They act like a delicate scaffolding within giant clouds of gas, providing a form of support that resists the relentless crush of gravity. This resistance can slow the collapse of a gas cloud, governing the pace at which new stars are born and even influencing the final sizes of those stars. The results are visible in the cosmos, with magnetic fields sculpting the long, flowing filaments and intricate pillars within nebulae, giving these stellar nurseries their iconic shapes. Beyond star formation, these magnetic lines act as cosmic highways for high-energy particles. They channel and confine dangerous cosmic rays, and they help transport energy and rotational momentum across vast distances, redistributing a galaxy's resources in a silent, continuous process. During the violent chaos of a galactic merger, these fields are not passive observers. They are stretched, twisted, and amplified to incredible strengths, becoming tangled throughout the colliding gas. This magnetic turbulence can influence the very dynamics of the collision, affecting how gas flows into the central regions and either fueling or suppressing the resulting firestorm of new stars. On a grander scale, the magnetic pressure contributes to the total pressure of the interstellar medium, helping to support the galaxy's structure against its own weight and regulating the overall balance between hot and cold gas. The origin of these pervasive fields remains one of astrophysics' great puzzles. The leading theory suggests a dynamo effect, where the slow rotation of the galaxy and the turbulent motions of its gas act like a giant generator, amplifying a weak primordial seed field over billions of years. This makes magnetic fields not a mere detail, but an integral character in the galactic story, an unseen architect working alongside gravity and dark matter to shape a galaxy's destiny from its first light to its final dimming. A galaxy's history is not written in books but in starlight. We have become cosmic archaeologists, sifting through the stellar populations of our own Milky Way to uncover its deepest secrets. Each star is a fossil, preserving a perfect record of the time and place it was born. Its chemical composition tells us what the galactic gas was made of. Its age reveals when it formed, and its motion through space traces the gravitational forces that have shaped it over billions of years. By analyzing the light from millions of these stellar fossils, we can perform a galactic dissection. We can separate the ancient, metal-poor stars of the halo, which are relics from the Milky Way's violent youth, from the younger, richer stars of the disk that formed in a more settled era. Incredible surveys like the Gaia mission are giving us the ultimate tool for this work, providing precise positions and motions for over 1 billion stars. This data is so powerful we can run the galactic clock backward, tracing the orbits of stars to reveal their origins. This is how we discovered the ghostly streams of stars arcing through our halo, the shredded remains of dwarf galaxies consumed by our own. It is how we can date the formation of the central bulge and map how different parts of the galactic disk were enriched with heavy elements at different times. This detailed forensic approach, star by individual star, allows us to test our grand theories of galaxy formation against the most intimate evidence possible. Our galaxy is no longer just a home, it is a historical document, and we are only just learning to read its ancient, luminous script. Your galactic address is as important as the galaxy itself. A galaxy floating in the quiet cosmic countryside, what astronomers call the field environment, lives a life of serene isolation. Here, a spiral galaxy can spin undisturbed for billions of years, its reservoirs of cold gas slowly and steadily coalescing into new stars. Its evolution is dictated primarily by its internal nature, its initial mass, and its spin. This is a galaxy living out its destiny with minimal interference, a cosmic hermit aging gracefully on its own terms. But a galaxy born into a dense urban cluster enters a world of relentless competition and violence. Its existence is one of constant gravitational harassment, swinging past neighbors at incredible speeds. This environment inflicts a brutal form of cosmic censorship. The thin, searing hot plasma that fills the space between galaxies acts like a powerful wind, and as a spiral galaxy moves through it, this ram pressure violently strips away its star-forming gas. The galaxy is robbed of its future, its spiral arms reddening and fading as its star formation is quenched in a relatively short cosmic time. Between these two extremes lies the group environment, a galactic suburbia. Here, small collections of galaxies, like our own local group, engage in a slow, gravitational dance. Interactions are more intimate and drawn out. A smaller galaxy may be tidally stretched and consumed by a larger one in a process astronomers call pre-processing, shaping it and stripping its gas before the entire group itself might one day fall into a vast cluster. This cosmic hierarchy forces a fundamental question: is a galaxy's fate predetermined by the mass of its dark matter halo, its innate nature, or is it sculpted by the nurture of its surroundings, the collisions and pressures it endures? The answer is a profound interplay of both. A galaxy's initial conditions set the stage, providing the raw materials and potential, but its environment writes the script, directing the drama of its life. A massive spiral galaxy will always be a massive system, but whether it remains a vibrant blue disk or is transformed into a red and dead elliptical depends almost entirely on the company it keeps. This reveals that a galaxy is not an island unto itself, but a citizen of a vast and dynamic cosmos, its story forever intertwined with the lives of its neighbors. The final chapter of our galactic story is not yet written, for our tools are evolving. A new age of discovery is dawning, powered by telescopes of such staggering power they will read the faintest whispers from the cosmic dawn. The James Webb Space Telescope is our newest time machine, its infrared gaze piercing the dust that shrouded our view for so long. It is capturing light from the universe's infancy, witnessing the first proto-galaxies as they flicker to life, mere fragments of stars and gas struggling to coalesce. We are seeing for the first time the raw, chaotic building blocks of the majestic spirals and ellipticals we know today. But to understand the full scope of galactic life, we must also look forward in time, observing the intricate dynamics of mature systems. This is the role of ground-based giants like the extremely large telescope. With a mirror nearly 40 meters across, it will not just see distant galaxies, it will dissect them. It will directly image planets in other star systems and measure the subtle motions of stars within nearby galaxies, revealing the invisible tug of dark matter with unprecedented precision. Yet another dimension of the story is written in cold, neutral hydrogen gas, the raw fuel for star formation. The square-kilometer array, a continent-spanning radio telescope, will map this faint radio glow across the entire sky. It will trace the cosmic web itself, watching vast rivers of gas flow into galaxies and powerful winds blow it back out, finally giving us a complete picture of the galactic life cycle from accretion to quenching. These observatories will work in concert, allowing us to watch galaxies evolve not as static snapshots, but as a continuous cosmic film. We will test our theories of black hole feedback by witnessing the outflows in action. We might even discover entirely new classes of galactic objects, phenomena we cannot yet conceive. The remaining gaps in our grand story of cosmic structure are about to be filled with light, promising answers to our oldest questions and, without a doubt, revealing mysteries we have not yet even learned to ask. The entire cosmic story unfolds like a single, breathtaking life cycle. It begins with the faintest quantum ripples, microscopic wrinkles in the fabric of the newborn universe. An unseen architect, dark matter, then amplifies these tiny seeds into a vast cosmic web, an invisible skeleton of deep gravitational wells. Into these wells falls the pristine gas of creation, hydrogen and helium, cooling and condensing over millions of years. This gas fragments, and within the darkness, the first stars erupt into being, their brilliant but brief lives ending in explosions that forge the first heavy elements and light the first proto-galaxies. These are the cosmic infants, small and chaotic, but gravity is a patient sculptor. Through relentless mergers and steady accretion, these initial fragments collide and combine, growing in size and majesty. Some settle into the stately rotation of majestic spirals, their arms traced by ongoing star birth. Others are forged in the violent fires of head-on collisions, their structures randomized into the smooth, round shapes of elliptical giants. This is the Hubble sequence in action, a living family album of galactic growth. A galaxy's dynamic life is then fueled from within by the continuous cycle of stellar birth and death, and shaped from without by its environment and the immense power of its central black hole. This supermassive heart acts as a cosmic thermostat, its violent outbursts capable of heating or expelling the galaxy's gas, ultimately quenching star formation to enforce a stable maturity. But all fuel runs out, whether gently through the slow exhaustion of its gas reserves or violently through environmental forces like ram pressure stripping. A galaxy's star-forming era eventually ends. Its vibrant blue glow of young stars fades, replaced by the steady red light of an aging population. The galaxy becomes a quiescent relic, a retired giant on the so-called red sequence. In the far, far future, even this red glow will dim. The last stars will exhaust their nuclear fuel, cooling into dark stellar remnants like white dwarfs, neutron stars, and black holes. These dark islands will drift in an ever-expanding, ever-cooling cosmos, a final, silent state known as the heat death. This is the secret life of galaxies, a grand narrative connecting the first spark of light to the final fade into darkness, a story written in gravity, light, and time itself. This grand cosmic cycle reveals a breathtaking truth about our own place in the universe. Every element essential for life, from the oxygen we breathe to the iron in our blood, was created in the nuclear furnaces of stars and scattered across space by their explosive deaths. We are not merely inhabitants of a galaxy, we are its direct descendants, built from the recycled remains of generations of suns that lived and died long before our own was even a spark. The astronomer Carl Sagan captured this profound connection when he said, "We are a way for the cosmos to know itself. Our very existence is a chapter in the ongoing story of galactic life, a story of transformation from the simplicity of hydrogen to the complexity of consciousness." This journey through the secret lives of galaxies, from their fiery birth in the dark ages to their quiet fade into the distant future, is ultimately a journey to understand our own origins. The frontier of this knowledge is expanding every day, driven by new telescopes and the relentless curiosity of those who look up at the night sky and wonder. We would love to hear which part of this galactic story captivated you the most. Was it the violent drama of colliding spirals, the mysterious influence of dark matter, or the profound finality of the heat death? Share your thoughts in the comments below, and if you are eager for more journeys to the edge of understanding, be sure to subscribe for our next exploration into the mysteries of space.